Page 216, section 3.1. All right, 3.1 is exponential functions. And I know you worked with exponents in Algebra 1 and Algebra 2, so we're fairly comfortable with these, but just good for us to review anyway. So they tell us on 216 that pretty much up to this point in our textbook, everything that we have worked with, or most of what we have worked with, have been algebraic functions. Algebraic function is just something that can be formed with algebraic processes, like adding, subtracting, multiplying, dividing, like polynomials. Quadratics, cubics, quartics, quintics that we've been solving by factoring and graphing and all of that type of thing. So primarily working with algebraics, but in Chapter 3, we want to look at exponential and logarithmic functions. They are not algebraic. They're actually something called transcendental functions. And so the definition they give us here on 216 of an exponential function is, it says the exponential function f with base of a can be denoted by f of x is equal to a to the x. So it's something like f of x is equal to 2 to the x, or y equals 2 to the x. That's an exponential function. Now, there are a few restrictions on that. Your a value has to be greater than 0, so your base is going to be a number greater than 0, and it can't be equal to 1. Because if you think about it, if this were 1 to the x, you would just get 1 no matter what you plugged in. So you would just have a horizontal line at 1, and that's not going to be what we find is the case with our exponential functions. The only restriction on your exponent is that that exponent x just has to be a real number. So it can be fraction, decimal, positive, negative, rational, irrational. It just can't be imaginary. Okay? So here are several examples here. Example number 1, they ask us to go through and evaluate each of these exponential expressions. So grab your calculator, graphing, scientific, whichever you want, and let's throw those in and see what we get. We're going to come up with decimal answers, so probably a good idea to round those to a couple of decimal places. In AP Calculus, we have to have everything to 3 decimal place accuracy or better. So that's a good default for us to just get into the habit of using. So let's round these to 3 decimal places. So if you have 2 to the negative 3.1, what are you getting for that? 0.117. Perfect. All right, how about 2 to the negative pi? 2 to the negative pi. What did you get for that? 0.113. All right, 12 to the 5/7.
5.8890, I guess.
No, 9. I got 5.90.
Yeah, so if we're rounding that one to 3 decimal places, 5.900. All right, how about 6/10 to the 3/2? 0.465. So everybody getting those to work? Good. Okay. So that's how we can evaluate our exponential expressions with our calculator. Now we want to look at graphing some exponential expressions. And we're actually going to look at 2 different setups. We're going to look at y equals a to the x and y equals a to the negative x. And in each of these cases, they're specifying that the a value they're referencing is a number greater than 1. Now, that's a little different than what we had up here. Up here we had a is greater than 0. So they have covered all of the possible values for a. When we've said a is greater than 0 and not equal to 1, we've got all those covered. Because over here, if you have a to the negative x, like let's say you had a to the negative 2. A to the, let's make the base 2. That'll be easier for us to see. 2 to the negative x. If you've got 2 to the negative x, that's the same thing as 1/2 to the positive x, right? So if we're talking about something written in the form of a to the x where a is greater than 0, this is going to cover all of our fractions, all of the numbers from 0 to 1, and this is going to cover all of the numbers greater than 1. So we will be catching all of those bases that are greater than 0. So sometimes in some textbooks, they'll write these 2 different setups as y equals a to the x where a is greater than 1, and over here they'll write this as y equals a to the x where a is a number between 0 and 1. Same idea as when we say a to the negative x where a is greater than 1. because when you have a negative exponent, that means you have to move it down to the denominator, and that would create that fraction, right? So whichever way you want to think of that, we've got all of our bases covered. So this first type, if we have y equals a to the x where a is greater than 1, that'd be something like f of x is equal to 2 to the x. We can graph anything on the face of the earth if we just plot enough points, right? So we could go through and make an xy chart for y is equal to 2 to the x. Maybe we want to plug in like 0, 1, -1, 2, -2, just try and get a feel, all right? So if we go through and we plug in positive 1, 2 to the 1 gives us 2. Plug in positive 2, 2 to the 2 gives us 4. Plug in 0, 2 to the 0 gives us 1. Plug in -1, 2 to the -1 is the same thing as 1 over 2 to the positive 1, so 1/2. And then -2, that's the same thing as 2 to the -2 is the same thing as 1 over 2 to the positive 2, so 1/4. So let's plot those points. And then we'll connect them. And when I do that, I have a pretty good idea of what's going on with this part of my graph up here. I mean, I could go ahead and put the arrowhead on the top and feel pretty comfortable that that's what that portion of the graph is going to continue doing. But I'm not really sure what's going on down here. Like, as I come down, I don't know if I'm going to like cross over and keep going down this way. It kind of looks like it's leveling off, so maybe there's a horizontal asymptote here. I'm just not really sure. I need to do a little more exploration. So let's keep coming over here. We had stopped at -2. Maybe I want to come over here and look at like -5 or -10 or something like that to get a better idea of what's going on. I'm actually going to look at -10 and -100, right? So if I were to put in -10, 2 to the -10 is the same thing as 1 over what? 2 to the positive 10, right? And so same idea, if I had -100, 2 to the -100 is the same thing as 1 over 2 to the 100. Positive divided by positive. No matter how far out here I'm going, it doesn't appear like this is going negative. This is still positive divided by positive. So I don't think, from this exploration anyway, I don't think that's going to cross over the x-axis and go down to negative values. Because no matter how far I kept going, I could plug in 10,000, a million, 10 million, a billion, and I'm still going to have a positive divided by a positive, right? So instead, if I go back and look at this 1 divided by 2 to the 10th, my numerator is staying the same. My denominator is getting bigger and bigger and bigger, right? I mean, 2 to the 10th is fairly large. 2 to the 100th is definitely large. My numerator is staying the same. My denominator is getting bigger and bigger, so what's the overall fraction doing? Getting smaller and smaller, right? So if my numerator is staying the same and my denominator is getting bigger and bigger and bigger, then this overall fraction is getting smaller and smaller. And that's even more true down here. This would be just a minuscule, tiny little value. So if my y value is getting smaller and smaller and smaller and tinier and tinier and tinier, but it's never going negative, then that just means that I'm getting closer and closer and closer and closer to that horizontal axis, but never crossing it. What is that? That's an asymptote, yes. So I'm going to have a horizontal asymptote for my function here. So now I have a pretty good idea that I know what that graph looks like. Now we're going to graph a lot of exponential functions. So if I have to do that every single time, that's going to get a little laborious. So let's look for some landmarks here, all right? When I graph an exponential function, I use 2 landmarks because there are 2 things that hold true the majority of the time. The first one is that I have a y-intercept at 0, 1. Think about why that's true. If you come up here and you put 0 in the place of x, any number raised to the 0 is equal to what? 1, with the exception of what? 0 raised to the 0 is undefined, right? However, I don't have to worry about 0 because it's not even going to be something I consider. A has to be a number greater than 0. So for all the numbers that I'm going to encounter, when I take any of those numbers and raise it to the 0, I'm always going to get 1. So that can be a landmark for me. That's a point that's going to be constant for me. in my initial exponential function. Now, if they shift it or reflect it or stretch it or shrink it, or, you know, if they contort my graph in some way, then that may not be true. But for my base function, my base exponential, that can be a landmark for me. The other landmark is what we just discovered right here by the work that we did, that I'm going to have a horizontal asymptote at y equals 0. Because it doesn't matter what this base was. If this base was 2 or 4 or 24, it would still hold true that my numerator would be staying the same and my denominator would be getting larger and larger, so that overall fraction would get smaller and smaller and never go to negative, so it would approach 0. So if I have those two landmarks, if they ask me to graph something like y equals 4 to the x, all right? If I'm graphing y equals 4 to the x, I can come over here and say, okay, no, I'm going to have a horizontal asymptote at y equals 0. No, I'm going to have an intercept at 0, 1. So I already know what this piece of the graph is going to look like. I honestly just don't know what this piece looks like. Like, it might be really steep and coming up here, or it might be, you know, pretty flat and coming out here, or it might look like this one. Honestly, I would just need 1 point to figure that out. So I'm going to come over here and I'm going to plug a positive 1 in to my function. So if I put 1 in the place of x, I'll get 4 for y. So I could say, okay, let's plot the point 1, 4, and literally I can draw a nearly perfect exponential function by plotting 1 point. So if I know those two landmarks, my y-intercept and my horizontal asymptote, and I know that basic shape, I'll literally be able to plot 1 point and have a nearly perfect graph. All right, let's look at the second scenario then. For our second scenario, we had y equals a to the negative x. Now, if you compare the original function with this function, the only difference is that negative right there. What does a negative usually cause in a function? A reflection, yeah, and you're right, it does also cause a fraction, as we were talking about with a negative exponent. But in terms of if you insert a negative into a function, it typically causes a reflection of some type, right? We've looked at two different types. When the negative is out in front of the entire function, that was reflection in the x-axis, right? But when the negative is just in front of x and then inserted into the function, that was reflection in the y-axis. So my first guess would be that if this is what the original function looks like, then if I have a to the negative x, then it would probably have some kind of a shape like this. But let's see. Let's make an xy chart again. If we've got f of x is equal to 2 to the negative x, again, let's just plug in 0, 1, -1, 2, -2. So if we plug in 1, 2 to the negative 1 is the same thing as 1 over 2 to the positive 1, so that'd be 1/2. Plug in 2, so 2 to the negative 2 is 1 over 2 to the positive 2, so 1/4. Plug in 0, 2 to the negative 0 is just 2 to the 0, that's 1. Plug in -1, so 2 to the negative 1 would be 2 to the positive 1, or 2. And plug in -2, so 2 to the negative 2, or 2 to the positive 2, would be 4. All right, so let's plot those points that we just got off of our XY chart. And sure enough, it does look to be lining up like we thought that it would, where it was that reflection in the y-axis. I have a pretty good idea of what this piece of the graph is doing over here. I might be a little skeptical as to what's going on down here in that thought process again of is it going to cross over the axis and come down here negative, but when I recognize that this function is the reflection of this function, then I know exactly what that piece of the graph is going to do. I also could come over here and plot some additional values like we had done over here to do some exploration with that as well. You'll notice that it maintains those same two landmarks. I still have a horizontal asymptote at y equals 0, and I still have a y-intercept at 1. Really, the difference is this entire function is increasing, where this entire function is decreasing. So an easy way to remember that is when I have the positive exponent, it's going up in the positive direction. When I have the negative exponent, it's going down in the negative direction. So increasing when it's positive, decreasing when it's negative. And we could do the same thing that we had done with that increasing function, where, okay, let's say they want me to graph 4 to the negative x. I could use my two landmarks and say, okay, I know I have a horizontal asymptote here. I know I have a y-intercept here. And I know the basic shape of my graph, that it's that decreasing function. So honestly, all that I don't know, I mean, I know this is going to approach that asymptote. So all that I don't know is over here how steep to make this. Like, does it come up like this, or does it come out like this, or does it kind of follow the path of the one that's there? So I just need 1 point. Only this time I need a point on the left-hand side. So maybe I plug in -1. So if I plug -1 into my function, minus the -1 would be +1. So at -1, I would get a y value of 4. Plot that point and connect, and I've got my graph. All right, so let's talk about the domain and range of our exponential functions. All right, let's start with domain. If we're looking at our increasing exponential function over here, what is our domain? All real numbers, right? Because if we're thinking about our x values for domain, you can see this is going to -infinity, and this is going to keep going and going and going and going and going. So yeah, we would have all real numbers there. -infinity to +infinity. How about range? Y is greater than 0, right? If you want that in interval notation, you could say 0 to infinity, or y is greater than 0, either one. All right. How about on the decreasing function? What's my domain? All real numbers. How about my range? Y is greater than 0, right? So the domain and the range don't change either. So when we get over to page 218, they give us a really good summary of what we've looked at so far. They tell us that when you're working with the graph of y equals a to the x, when a is a number greater than 1, that your domain is going to be -infinity to infinity, your range is going to be 0 to infinity, your intercept is going to be 0, 1, the entire function will be increasing, your horizontal axis will be the horizontal, your horizontal asymptote will be at the horizontal axis, the x-axis, y equals 0. And the entire function will be continuous. Now, that's a term we had seen before. It just means that it's a smooth connected curve. It doesn't have holes or skips or jumps in it. I can draw it without picking up my pencil, basically. All right? Then for y equals a to the negative x, they tell me all of the same things. The only difference is that this is a decreasing function, and they show me pictures of those two graphs. Okay? So the only thing that I would point out to you is that there are 1 or 2 homework problems that don't immediately appear to fit into either of those scenarios. Like, let's say they gave me something like y equals 3/5 to the x. And I look at that and go, well, 3/5, that's like less than 1. And they told me that in each of these cases, a has to be greater than 1. So it doesn't immediately look like it fits those scenarios. But if I go back to the description of an exponential function just says that a has to be greater than 0. Yep, 3/5 is greater than 0. That's good. And x has to be any real number. So as long as I just plug real numbers in here and not imaginary, then yeah, that's an exponential function. So 2 ways that I could go with this. Number 1, I could say, I know my 2 landmarks for an exponential function. It has to have a y-intercept at 1, has to have a horizontal axis at 0. I just don't know if it's an increasing function or decreasing function. Okay, well maybe instead of plotting 1 point, I might have to plot 2. So I plot 2 points to figure out if it's going up or down. Not a tragic thing. Maybe I plug in +1 and -1, and then I've got it. The other thing that I could do is it does fit one of these 2 scenarios. It's just kind of in disguise. Because if I take 3/5 and I rewrite that as 5/3, that would be 5/3 to the negative x, then you can see it does fit that scenario. A is greater than 1, and so that's going to be one of those decreasing functions. So we had mentioned in the very beginning that when they tell me a just has to be a number greater than 0, that this will take care of all of the numbers that are greater than 1, and this function over here is the what they would use to cover the values between 0 and 1. So that's what we were seeing right here. The 3/5 to the x is the same thing as 5/3 to the negative x. That covers the values between 0 and 1. So your option is, if you want to rewrite it so that it fits one of those two scenarios, fantastic, go ahead. But you also could work with it as it is, since you know it's an exponential function and you know its landmarks. You'd only have to make an XY chart with maybe two values and you'd still be able to get everything that you need. So either way you want to go there. Just wanted to mention those to you since they're a little atypical. All right, so once they've explained to me about what the base functions for exponentials look like, then they're going to put them back in combination with the things that we've seen before, like shifting, reflecting, stretching, shrinking, all of those types of things. So look at example number 4. For example number 4, it says if f of x is equal to 3 to the x, if that's our base function, then let's go through and let's see what all of these different changes will do to that function. So first off, we need to start with the base function, all right? So if I've got f of x is equal to 3 to the x, I know that I have two landmarks, right? I have a y-intercept at 1, I have a horizontal asymptote at the x-axis. Is that the increasing function or the decreasing function? Increasing. So I also know that its basic shape is going to be like this. So I know what this piece looks like if I have my intercept and I'm approaching that asymptote. I just don't really know how steep to make this other side over here. So as we said, I just need to plot 1 point to get a nearly perfect graph. So I'm going to go through and plug in +1. So if I put +1 in the place of x, I'm going to get 3. So if I plot the point 1, 3, that'll tell me how steep to make that. So there's my base function. We had done 2 to the x and 4 to the x. Here's 3 to the x. Works just like that. All right. So then for g of x, they put in this +1. What does that +1 cause? All right. It causes a shift. What kind of shift? Horizontal or vertical? All right. That 1, can you move that to the other side? No, it's stuck to the x, right? Because it's up in the exponent, it's attached to the x. It can't be moved to the other side. It can't be subtracted from y. It has to be subtracted from x. So any value subtracted from x is a horizontal shift. So we have a horizontal shift of what? -1, right. So if I have a horizontal shift of -1, here's what I'm going to do. If I had a horizontal asymptote right here, if you horizontally shift that a -1, does that affect that at all? No, still there. So then I can take the other 2 points that I had used to draw my original function and just horizontally shift them a -1. So take this and come over 1, and take this and come over 1, and I have everything I need to draw my graph. All right, look at h of x. For h of x, what is that -2 going to cause? Vertical shift, because that can be moved to the other side, right? That is not attached to the x. It's not up in the exponent. So if I move that to the other side, that would be y + 2. So what's being subtracted from y? What's my vertical shift? -2, right. So if I have a vertical shift of a -2, I had a horizontal asymptote here, is that going to affect my horizontal asymptote?
Yes.
Yeah. If you have a horizontal line and you're supposed to take your whole graph and bump it down 2, absolutely that's going to affect my asymptote. So if my asymptote was at 0 and I have a vertical shift of -2, where's it going to be? At -2, exactly. So I'm going to take my landmark, that's my horizontal asymptote, and move it down 2. I'm going to take my landmark of my y-intercept and move it down 2. And then I'm going to take that other point that we had found to help us with our graph, and I'm going to move it down 2. And now I have everything I need to sketch my graph. All right, for k of x, what happens when we put a negative out in front of the whole function? What does that cause? Reflection, right? Reflection in what? Reflection in x, right? Negative out in front of the entire function is a reflection in the x-axis. So again, I'm going to take that original graph that we had, and I'm just going to reflect it in the x-axis. So I had an intercept at +1, now that intercept is at -1. I had a point up here at 1, 3, now I have a point at 1, -3. And my asymptote is still the same, so I have everything I need to sketch that graph. All right, then for j of x, instead of the negative being out in front of the function, the negative is just in front of x, so what is that? reflection in the y-axis, right? So if I take my original function and I reflect it in the y-axis, my horizontal asymptote is still the same, my intercept is still the same, but the point 13 has now become the point -13. The other way that you could look at that is that's just our second scenario from today, right? When you had 3 to the negative x, that was the decreasing function that had the y-intercept and the horizontal asymptote as the two landmarks. And then we just picked one extra point, like we took -1 and plugged it in, and that would have given us the +3, and we could have gotten it that way as well. So you can see those two different concepts, the old that we already know and the new that we've picked up today, give us the exact same thing, reinforcing each other. Okay? All right, so here is our homework for tonight on pages 225 to 226. 225 to 226.